Before we begin, a critical safety disclaimer. This video is for educational purposes only. Commercial ovens involve high-voltage electricity, natural gas or propane, and extremely high temperatures, all of which can cause serious injury, death, or property damage if handled improperly. Always disconnect all power sources and shut off the gas supply before attempting any inspection or repair. If you are not completely confident and qualified to perform these tasks, please hire a licensed professional. Your safety and the safety of your staff is the #1 priority. It's 7 a.m. on a Saturday. The line is already starting to snake out the door. The smell of fresh coffee is in the air, but the smell of baking bread is gone. You feel a cold pit in your stomach as you rush to the back. The fans on your main convection oven are silent. The heating element is cold. You flip the switch off and on again. Nothing. You just stared at a $50,000 piece of equipment that has suddenly become a giant, useless metal box. Every minute it sits there, cold and dead, you're not just losing sales on croissants and muffins, you're losing customers, you're losing your reputation, and you're losing your mind. That panicked phone call you're about to make? The one to the emergency repair service? That's going to cost you, on average, over $900. That's just for the visit. That doesn't include parts, and it certainly doesn't include the thousands of dollars in revenue you're bleeding out while you wait for a technician who might not even show up for another 4 hours. This video and this entire series is designed to end that nightmare. We are going to pull back the curtain on commercial oven repair. I'm going to show you how to diagnose and fix the most common problems that plague small business owners, from pizzerias to bakeries to high-volume restaurants. We're not talking about rebuilding a motor from scratch. We're talking about replacing a faulty thermostat, a bad igniter, or a worn-out door gasket. The issues that account for 80% of all service calls. We're going to turn that feeling of helpless panic into a feeling of confident control. We're going to turn a $1,000 emergency bill into a $50 part and an hour of your time. This is your guide to taking back power over the single most important piece of equipment in your kitchen. This is your path to saving thousands, maybe even tens of thousands of dollars over the life of your business. So where do we start? We don't start with a wrench. We don't start by pulling off panels. We start with the most important tool you will ever own. A safety-first mindset. It sounds boring, but ignoring it is what separates a simple repair from a trip to the emergency room or a call to the fire department. There are two main dangers we're dealing with: electricity and gas. Let's talk electricity first. Your commercial oven is likely running on 208 or 240 volt, three-phase power. This is not the same as the outlet your phone charger is plugged into. This is serious industrial-grade power that can kill you instantly. Before you even think about touching a screwdriver, you need to find the circuit breaker for that oven. It should be clearly labeled in your breaker box. You're going to switch it to the OFF position. But we don't stop there. You need to physically lock it out. You can buy a simple breaker lockout device for a few dollars online or at any hardware store. You snap it onto the breaker, and you put your own padlock on it. This is called a lockout/tagout procedure. It ensures that nobody, not a well-meaning employee, not a cleaning crew, nobody, can accidentally flip that breaker back on while you're working with live wires. Your life depends on it. Next, gas. Whether you're on natural gas or propane, you need to know where your gas shutoff valve is. For most ovens, there's a yellow-handled valve on the gas line right behind the unit. You turn it so the handle is perpendicular to the pipe. That's it. Gas is off to the oven. But you should also know where the main gas shutoff is for your entire building. Know it, find it, and make sure it's accessible. If you ever smell gas, that distinct rotten egg smell, you don't try to find the leak. You get everyone out of the building immediately and call 911 and your gas company from a safe distance. The final safety step is heat. Sounds obvious, but you'd be surprised. An oven that was just running at 450 degrees can hold that temperature for a long, long time. Always give the oven ample time to cool down completely before you start working on it. A severe burn can be just as debilitating as an electric shock. Okay, our safety mindset is locked in. Now let's understand what we're actually working on. While there are dozens of brands, most commercial ovens fall into three main categories: convection, deck, and conveyor. First, the convection oven. This is the workhorse of most bakeries, restaurants, and catering kitchens. Think of it as a supercharged version of your oven at home. It has heating elements, but it also has a fan, or sometimes multiple fans, that circulate the hot air. This hurricane of heat cooks food faster and more evenly. When a convection oven fails, the problem is often related to either the heating elements, the thermostat that reads the temperature, or the fan motor that moves the air. Second, the deck oven. This is the king of pizza and artisan bread. A deck oven doesn't use fans. It uses intense, radiant heat from stone or steel decks, above and below the food. Think of it like cooking on a very, very hot rock. They create that perfect, crispy crust. Common failures here often involve the thermostat, the safety valves that control gas flow, or the igniters that light the burners under those decks. They are simpler mechanically than a convection oven, but the temperatures are often much higher. Third, the conveyor oven. If you're running a high-volume pizza chain or a sandwich shop, you probably have one of these. Food goes in one side on a metal conveyor belt, travels through a tunnel of intense heat, and comes out the other side perfectly cooked. They are masters of consistency and speed. The problems here can be a bit more complex. You still have heating issues, but now you also have a motor, a gearbox, and a chain that moves the belt. A conveyor oven not heating is one problem. A conveyor oven that's not conveying is a whole other beast. Knowing which type of oven you have is the first step in diagnostics. A problem with a fan motor can only happen in a convection oven. A problem with a conveyor belt can only happen in a conveyor oven. It narrows down the possibilities immediately. Now, before we can fix anything, we need the right tools. You don't need a giant $10,000 rolling toolbox. You can build a powerful, effective oven repair kit for under $100. The single most important tool you will buy is a good multimeter. Let me say that again. A good multimeter. This is your magic wand. It allows you to see electricity. It tells you if power is getting where it needs to go, if a switch is working, or if a heating element has burned out. You can't guess with electricity, you have to test. We'll do a deep dive on how to use one in the next part, but for now just know you need one. Get a digital one with settings for AC and DC voltage, continuity, and resistance. Next, a good set of nut drivers, both in metric and imperial sizes. A huge percentage of the screws and bolts inside an oven have hex heads. A nut driver is like a screwdriver for bolts, and it's 1,000 times faster and easier than fumbling with a tiny wrench in a tight space. You'll also need a basic socket set, a good set of Phillips and flathead screwdrivers in various sizes, a pair of needle nose pliers, and a pair of wire strippers. For gas-related work, you'll want 2 pipe wrenches, one to hold the pipe, one to turn the fitting, and a bottle of gas leak detection solution. It's basically a special soap bubble mixture that will instantly show you if a fitting is leaking. That's it. That's your starter kit. A multimeter, nut drivers, screwdrivers, pliers, and wrenches. With this small arsenal, you can perform the vast majority of common repairs. You've invested in your tools, you've established a safety-first mindset, and you understand the basic DNA of your machine. You are no longer just a business owner at the mercy of your equipment. You are becoming a first responder for your kitchen. You are building the confidence to face that 7 a.m. Saturday morning disaster not with panic, but with a plan. And that plan begins not with a wrench, but with a mindset. The mindset of a professional. Before a pilot ever touches the controls, they do a walk around. Before a surgeon makes an incision, they scrub in. And before you ever open a single panel on your commercial oven, you must commit to a non-negotiable, life or death principle. Safety first, safety last, safety always. This isn't the boring part you skip. This is the part that keeps you in business and, more importantly, keeps you alive. We are dealing with the holy trinity of industrial danger: high-voltage electricity, combustible gas, and extreme heat. There are no second chances with any of them. So, rule number 1, the absolute golden rule, is to de-energize the equipment. And I don't mean just turning the knob to off. Turning a dial is a suggestion. Killing the power is a command. You need to know with 100% certainty where the power source for your oven is. For an electric oven, this means finding the dedicated circuit breaker in your electrical panel. That big gray box on the wall in the back room? It's time to get acquainted. Find the breaker labeled for your oven. If it's not labeled, now is the time to figure it out and label it yourself with a bold, permanent marker. When you go to work on the oven, you don't just flip it, you lock it out. You can buy a simple, cheap breaker lockout device online. It clamps onto the breaker switch and you put a padlock on it. This physically prevents anyone from accidentally turning the power back on while your hands are inside the machine. It's what the pros do, and now it's what you do. For a gas oven, you have 2 things to worry about. You still have electricity running the fans, the controls, the igniter, so you still perform the exact same electrical lockout procedure. But you also have gas. You need to find the gas shutoff valve for your oven. It's usually a yellow or red handle on the gas line behind the unit. You turn it so the handle is perpendicular to the pipe. That's it. Gas off. You do both every single time. No exceptions. No, I'm just checking one little thing. Because the moment you get complacent is the moment 1,000 volts of electricity or a cloud of natural gas reminds you who's boss. The second part of your pre-flight check is to know your machine's identity. Every commercial oven has a birth certificate. It's called a data plate or a rating tag. It's a small metal plate, usually riveted to the side, back, or inside the door jamb. You need to find it. Right now. Go look for it. This little plate is the Rosetta Stone for your oven. It contains the 3 most critical pieces of information you will ever need: the model number, the serial number, and the voltage and fuel type. Why is this so important? Because a Blodgett convection oven isn't an identity. That's like saying, I drive a Ford. Is it a Focus? An F-150? What year? What engine? Without the model and serial number, you are flying blind. You can't order the right parts. You can't look up the correct wiring diagram. You can't even call a technician for advice and give them the information they need. I've seen countless small business owners waste hundreds of dollars in days of downtime because they ordered a gas valve for a model G100 when they actually had a G100B, and the part is completely different. Find that plate. Take a clear, well-lit photo of it with your phone. Email it to yourself. Print it out and tape it to the wall next to the oven. Engrave it into your memory. That model number is your key to the kingdom. Now that we've covered safety and identification, let's build your toolkit. Your first aid kit. You don't need a $10,000 rolling toolbox, but you do need a few essential high-quality items that will pay for themselves the very first time you use them. This isn't an expense. It's an investment in uptime. First and most important, a multimeter. This is the single most powerful diagnostic tool you will ever own. It looks intimidating with its dial and probes, but it's really just a doctor's stethoscope for your oven. It lets you listen for the heartbeat of electricity. It tells you with absolute certainty if power is present, if a switch is working, or if a heating element has failed. It turns guesswork into facts. You don't need a fancy one. A basic, reliable digital multimeter from a hardware store is all you need to start. We will dedicate an entire future part of this series to using it step by step, but for now your only job is to buy one. Get it in your hand. It's your Excalibur. Next, you need drivers. Not just one screwdriver. You need a set. A good multi-bit screwdriver is a great start. Make sure it includes multiple sizes of Phillips and flathead bits. But here's the pro tip. Make sure it also includes Torx bits. Those are the ones that look like a 6-pointed star. Manufacturers love using Torx screws on access panels specifically to keep people like you out. But you're not just people anymore. You're the first responder. So get the Torx bits. You will also want a set of nut drivers, specifically a 1/4 inch and a 5/16 inch. A massive percentage of the screws and bolts inside a commercial oven are one of these 2 sizes. Having the right nut driver is the difference between a 5-minute fix and a 2-hour struggle with a pair of pliers. Speaking of pliers, you need 2 kinds. A pair of needle nose pliers for reaching into tight spots and manipulating small wires and connectors. And a pair of channel lock pliers for a firm grip on larger nuts, bolts, and fittings. Don't cheap out here. A good grip is a safe grip. You also need to see what you're doing. The inside of an oven or the space behind it is dark. Your phone flashlight is okay in a pinch, but it's a pain to hold while you're trying to work. Get a good bright headlamp, the kind that straps to your forehead. It puts brilliant light exactly where you are looking and keeps both of your hands free to work. It feels a little dorky the first time you put it on, but when you're deep in the guts of a machine, it feels like a superpower. Finally, the most underrated tool in your entire kit is already in your pocket: your smartphone. Before you unplug, unscrew, or unclip a single thing, take a picture of it. Then take another picture from a different angle. Take a short video. You think you'll remember how those 5 colored wires connect to that terminal block? I promise you an hour later you won't. Your phone is your external brain. It's a perfect, infallible memory of how things are supposed to look. Costs you nothing and it will save you from catastrophic mistakes. So let's recap the plan. 1. You have a non-negotiable safety protocol. Power off, locked out, and gas off. Every time. 2. You know your oven's true identity. You have a picture of that data plate, and you understand that the model and serial number are your lifeline. And 3. You've assembled your essential toolkit: a multimeter, a versatile set of drivers including Torx bits, 1/4 inch and 5/16 nut drivers, 2 types of pliers, a headlamp, and your phone. This is your foundation. This preparation is what separates a panicked amateur from a calm, collected problem solver. You haven't even diagnosed a problem yet, but you've already won half the battle. You've replaced chaos with process. You've built your workbench and laid out your instruments. You're ready. Now that you're armed with the tools and the safety mindset of a professional, it's time to learn how to listen. Because when your oven fails, it's trying to talk to you. Every strange noise, every error code, every dish that comes out burnt on one side and raw on the other. These aren't just problems. They are clues. And you are about to become a detective. Your first mission, should you choose to accept it, is to assemble your detective's kit. This isn't about running to the hardware store and buying a 100-piece socket set you'll never use. This is about precision. It's about having the right tools to uncover the truth. Think of it as your go bag, the essential gear you need to crack any case that comes across your desk or out of your kitchen. First and most importantly is your lie detector, a multimeter. If you buy only one tool, this is it. It doesn't need to be a $1,000 fluke meter. A simple $20 digital multimeter from any big box store will do. This little device is your superpower. It lets you see the invisible world of electricity. It tells you if power is flowing where it should be, and just as critically, if it's not. It can tell you if a part is lying about being functional or telling the truth about being broken. Without it, you're just guessing. You're a detective showing up to a crime scene without a fingerprint kit. We'll learn exactly how to use it later, but for now, know this. The multimeter separates the amateurs from the pros. Get one. Next, you need a good set of screwdrivers. Both Phillips head and flathead. But don't just grab the ones from your junk drawer. Get a set with comfortable, insulated handles. You'll be working in tight, awkward spaces, and the last thing you want is a cheap screwdriver stripping a screw head, turning a 10-minute job into a 2-hour nightmare. Get a few different sizes, including a shorter, stubby one. You'll thank me when you're trying to remove a panel with only 3 inches of clearance. Along with screwdrivers, you'll need a set of nut drivers. Specifically, 1/4 inch and 5/16. A massive percentage of the fasteners inside a commercial oven are one of these 2 sizes. A nut driver is like a screwdriver for nuts and bolts. It's faster and provides better torque than fumbling with an adjustable wrench in a tight spot. Having the right size on hand feels like having a key to a secret door. Now for your senses. You need to enhance them. Get a good flashlight. Not the one on your phone. A dedicated, bright LED flashlight, maybe even a headlamp. Ovens are dark, cavernous places. The clue you're looking for, a burnt wire, a tiny crack in a ceramic insulator, is hiding in the shadows. You need to be able to light up every corner like it's daytime. A small inspection mirror like a dentist uses is also a game changer. It allows you to see around corners and behind components without having to be a contortionist. It's your periscope into the hidden world of your oven's internals. Finally, a few simple but crucial items. A pair of needle-nose pliers for grabbing wires and manipulating small parts. A wire stripper because you may need to make a clean connection. And some heat-resistant gloves. We're dealing with ovens, and even after they've cooled, some parts can hold a surprising amount of residual heat. That's it. That's your starting kit. A multimeter, screwdrivers, nut drivers, a flashlight, a mirror, and some pliers. With these tools, you can diagnose and solve the vast majority of common oven problems. Now that you have your kit, we need to talk about the single most important rule of this entire operation. It's the first thing any real detective learns. Secure the scene. Before you ever open a panel, before you ever touch a wire, you must ensure your own safety. Your oven is not your friend right now. It's a 1,000-pound box of metal with 3 different ways to seriously hurt you. High voltage electricity, combustible gas, and intense heat. We respect the machine, but we do not trust it. First, electricity. You must kill the power. And I don't mean just turning the oven off at the switch. That's not good enough. You need to go to your breaker box and shut off the circuit breaker that controls the oven. Find it, flip it to the off position, and then this is critical. Put a piece of tape over it with a note that says, "Do not turn on." You might be the only one working, but you never know when someone might come along, see a trip breaker, and flip it back on out of habit. Treat every wire inside that oven as if it's live, even after you've cut the power. Why? Because of capacitors. Some components can store a lethal electrical charge long after the power is off. They are like a hidden trap, waiting for an unsuspecting hand. Your multimeter is your best friend here. You can use it to safely test and confirm there is zero, and I mean zero voltage before you begin your work. Second, if you have a gas oven, you must shut off the gas. There will be a gas valve on the line leading to your oven, usually with a yellow or red handle. The handle will be parallel to the pipe when it's open. You need to turn it a quarter turn so it's perpendicular to the pipe. That's the off position. If you ever, for any reason, smell that rotten egg smell of natural gas, stop everything. Do not turn anything on or off. Do not create a spark. Leave the building immediately and call your gas company or the fire department from a safe distance. There is no repair worth risking an explosion. Period. Third, heat. This seems obvious, but you'd be surprised. Let the oven cool down completely. And I mean completely. Hours if necessary. Metal components, insulation, and ceramic parts can hold on to heat for a very long time. A severe burn can take you out of commission for weeks, and that's the last thing your business needs. Okay, the scene is secure. Power is off and locked out. Gas is off. The machine is cool. Now your investigation can truly begin. The first step is to gather evidence. What was the oven doing or not doing just before it failed? This is your witness interview. Think back. Were there any strange sounds? A healthy oven has a rhythm. The hum of a fan, the solid thump of the gas valve opening, the gentle tick-tick-tick of an igniter. Has a new sound appeared? A high-pitched whine? A grinding or scraping noise? That's a clue. A motor bearing might be failing. A fan blade could be hitting something. What about the performance? Is it not getting hot enough? That points to a problem with the heating element or the igniter. Is it getting too hot, burning everything? Now your primary suspect is the thermostat, the very component that's supposed to regulate temperature. Is the heat uneven? Are pizzas coming out with one side perfectly cooked and the other pale and doughy? That screams that your convection fan isn't working, failing to circulate the hot air. And don't forget your nose. Your sense of smell is a powerful diagnostic tool. The sharp, acrid smell of burning plastic or electrical insulation is a giant red flag that a wire is shorting out or a motor is overheating. The smell of unburnt gas when the oven should be lit means your igniter is failing to do its one job: create a spark. Once you've gathered these initial clues, the sounds, the smells, the performance issues, you can start to build a profile of your culprit. In the world of oven repair, there's a lineup of usual suspects, a handful of components that are responsible for 90% of all failures. Let's meet them. First, you have the heating element in an electric oven, or the burner assembly in a gas oven. This is the muscle of the operation. Its job is simple: get hot. When it fails, it either doesn't get hot at all, or it develops hot spots, creating uneven cooking. Visually, you might see a break or a blister in an electric element. Next is the igniter. This is the spark of life for a gas oven. It's a small, fragile component that glows incredibly hot to ignite the gas. They are notoriously brittle and have a finite lifespan. When they start to fail, they get weak. They might glow, but not get hot enough to open the gas valve, leading to an oven that won't light. Then there's the thermostat or the thermocouple. This is the brain. It's a sensor that reads the temperature inside the oven and tells the heating elements or burner when to turn on and off. If the brain is faulty, it might think the oven is cold when it's hot or hot when it's cold. This leads to wild temperature swings, or an oven that never shuts off, burning everything to a crisp. Don't forget the convection fan motor. This is the circulatory system. Its job is to move the hot air around for even baking. If this motor dies, you lose that circulation. Hot air will just sit, creating a much hotter zone at the top of the oven and a cooler zone at the bottom. This is the classic culprit for that burnt on top, raw on the bottom problem. Finally, you have the big boss, the control board. This is the electronic mastermind that controls everything. The timers, the temperature settings, the error codes. If the control board goes bad, you can have all sorts of bizarre problems, or the oven might just appear completely dead. It's often the last thing you should suspect, because it's the most expensive to replace, but it's always a possibility. These are your 5 primary suspects: the element, the igniter, the thermostat, the fan, and the board. Your clues, the sounds, the smells, the performance failures will point you toward 1 or 2 of them. You've secured the scene, you've gathered your evidence, and you've identified your suspects. Your investigation is officially underway. And in the next part, we're going to do something truly powerful. We're going to take our number 1 tool, the multimeter, and use it to interrogate our number 1 suspect. We're going to learn how to prove, beyond a shadow of a doubt, whether a part is guilty or innocent. The multimeter doesn't have an opinion, doesn't guess. It deals in the cold, hard currency of electricity: volts, ohms, and continuity. And by understanding its language, you can get a confession out of any component in your oven. So let's get fluent. First, let's meet the team. You have the multimeter itself, the brain of the operation. And you have two probes, usually a red one and a black one. These are your hands. They are how you'll interact with the machine's nervous system. The black probe almost always goes into the port labeled COM for common or ground. The red probe typically goes into the port with a V, and the Greek letter omega for ohms. Don't worry about the other ports for now. They're for more advanced tests we don't need. We are going to learn 3 fundamental tests. 3 questions that will solve 90% of your electrical problems. Think of it as a detective's checklist at a crime scene. Question number 1. Is there a complete path? This is the continuity test. Question number 2. Is power actually getting to the suspect? This is the voltage test. And question number 3. Is the suspect behaving correctly? This is the resistance or ohms test. Let's start with the simplest, most powerful test in your arsenal, the continuity test. Continuity just means, is there an unbroken path from point A to point B? Imagine a bridge over a river. If the bridge is complete, cars can cross. If there's a giant hole in the middle, they can't. Electricity is the same way. It needs a complete, unbroken bridge of wire or metal to flow. A heating element is a bridge. A fuse is a bridge. A switch is a bridge that you can open and close. The continuity test is simply you yelling across the river, "Hey, is the bridge intact?" Your multimeter gives you a beautiful, simple way to get the answer. It beeps. First, and this is the most important safety rule for this test, the power must be OFF. Not just turned off at the switch, but the oven must be completely unplugged from the wall. We are not checking for live power. We are just checking the integrity of the bridge itself. Doing this with the power on can destroy your meter and, far worse, could seriously injure you. So unplug the oven. Double check it. Now, turn the dial on your multimeter to the continuity setting. It usually has a symbol that looks like a sound wave or a series of parallel arcs. Sometimes it shares a spot on the dial with a diode symbol, which looks like an arrow pointing at a line. To make sure it's working, touch the metal tips of your red and black probes together. You should hear a beep. Clear instant beep. That sound is the sound of a complete path. You've just created a tiny, perfect bridge between your 2 probes, and the multimeter is celebrating. If you don't hear a beep, check your connections or the battery in your meter. Never trust a silent meter. Okay, so how do we use this? Let's take a simple fuse. A fuse is designed to be a weak link, a sacrificial bridge. If too much power tries to cross, it burns out, breaking the path and protecting more expensive components. But sometimes you can't tell if it's blown just by looking at it. With the oven unplugged, you take your probes and touch one to each metal end of the fuse. If you hear that beautiful beep, the bridge is intact. The fuse is good. It is innocent. You can move on. If you get silence, dead absolute silence, the bridge is out. The fuse has done its job and sacrificed itself. It's guilty of being blown. You've found your first culprit. It's that simple. A beep means it's good. Silence means it's bad. This works for switches, thermostats, and wires. You are testing if the path itself is broken. Now for question number 2, and this one requires your absolute, undivided attention because we are now dealing with live electricity. This is the voltage test. The continuity test told us if the bridge was intact. The voltage test tells us if any cars are actually being sent towards the bridge. This is maybe the most common mistake a beginner makes. They find a part like a motor or a heating element that isn't working. They test its continuity, they get silence, and they assume the part is bad. They order a new one, spend hours installing it, turn the oven on, and nothing. The new part doesn't work either. Why? Because the problem wasn't the part. The problem was that no power was ever getting to it in the first place. They replaced a perfectly good bridge when the real problem was that the main highway leading to the bridge was closed 5 miles up the road. The voltage test prevents this. It answers the question, is power, the motive to do work, present at the component? For this test, the power must be on. The oven must be plugged in and turned on to a setting that should be activating the part you're testing. This is not a suggestion. This is a fundamental rule. We are measuring live electricity, so every single safety precaution applies. Be steady. Be focused. Know where you're going to put the probes before you go in. Never let your hands touch the metal tips of the probes. Turn the dial on your multimeter to AC voltage. The symbol is AV with a wavy line next to it. V with a straight line is for DC like batteries, which we rarely deal with in the power section of an oven. Most commercial ovens in the US run on 240 volts, so you'll want to set your meter to a range that can handle that. Usually a 600 V setting is a safe bet. Let's say we're testing a bake element. It's not heating up. We need to know if it's getting the 240 volts it needs to do its job. With the oven on and set to bake, we carefully touch one probe to one terminal where the power wire connects to the element, and the other probe to the other terminal. You look at the screen. If you see a number at or around 240 volts, then you know power is being delivered. The highway is open. The electricity is arriving, but the element isn't doing its job. Now you know the element itself is the likely suspect. But if you do that test and the meter reads 0 or a number very close to 0, you've just discovered something profound. The element isn't the problem. It can't be guilty of not working if it was never told to work in the first place. The problem lies upstream, in the thermostat, the relay, the control board, or the wiring. You just saved yourself the cost of a new element and the headache of replacing it for no reason. This one test separates the amateurs from the pros. Finally, detective question number 3, the resistance test. This one is subtle, but it's what catches the most clever criminals. Continuity told us if the path existed. Voltage told us if power was present. Resistance tells us about the quality of that path. It answers the question, is the component doing its job correctly? Like the continuity test, for this test, the power must be off and the oven unplugged. I will say it again. Unplug the oven. Resistance, measured in ohms, is the measure of how much a component fights against the flow of electricity. Some components, like a wire, should have almost zero resistance. Others, like a heating element, are designed to have a very specific amount of resistance. That resistance is what generates the heat. Think of it like a nozzle on a hose. A wide-open hose has low resistance to the water. A narrow nozzle has high resistance, and the water sprays out with more force. A heating element needs a specific nozzle size to work right. If its internal wiring starts to break down, its resistance can change. To test it, you turn your multimeter dial to the ohm setting, which is marked with the Greek letter omega. Then it's best to disconnect at least one wire from the component you're testing to make sure you're only measuring the component and not other parts of the oven circuitry. You touch your probes to the two terminals of the heating element, just like you did for the continuity test. But instead of listening for a beep, you're looking for a number. Now, what number should you see? This isn't a simple good or bad like a fuse. You need to know what the resistance should be. You can usually find this information in the oven's technical manual, or by looking up the part number online. Let's say the spec sheet says your element should have 25 ohms of resistance. If you measure it and you get a reading very close to 25 ohms, then the component has a good character. It's behaving as expected. It's probably innocent. If you get a reading of OL, which means overload or open line, that's the same as infinite resistance. The bridge is completely out. This is the same result you get from a failed continuity test. The part is definitely bad. But here's the tricky part. What if you measure it and get 100 ohms? Or 5 ohms? The path exists, it would probably pass a continuity test, but it's not the right path. Its character is flawed. An element with resistance that's too high won't get hot enough. One with resistance that's too low might draw too much current, tripping breakers or causing other damage. This component is guilty. It's lying about its ability to do the job properly, and the resistance test is the lie detector that caught it. So there you have it. The 3 key interrogation techniques. Continuity, is the path there? Voltage, is power arriving? Resistance, is the path performing correctly? By mastering these 3 simple tests, you can walk up to almost any dead oven, and within minutes begin to uncover the truth. You can stop guessing and start knowing. You can stop wasting money on parts you don't need and start fixing problems with the confidence of a seasoned detective. Now that we know how to interrogate a suspect, it's time to identify our first one. In the world of commercial ovens, the most common failure, the usual suspect we always line up first, is the heating element itself. And in the next part, we're going to put it on trial. We're going to take everything we just learned and apply it to a real-world bake element step by step. The theory is over. It's time to get our hands dirty. Alright, here it is. The suspect. This is a standard bake element, pulled from a workhorse convection oven you'd find in 1,000 different bakeries, cafes, and small restaurants across the country. And right now it's accused of murdering your profits, your productivity, and your patience. Our job is to determine its guilt or innocence. And the tool we're going to use to conduct our interrogation is this, the multimeter. This little box is our lie detector. It doesn't care about excuses. It only deals in electrical truth. Now, before we lay a single finger on this element or this oven, we have to talk about the single most important rule. The one unbreakable law of this entire process. You absolutely must kill the power. I don't mean just turning the oven off at the dial. I mean go to your breaker panel, find the one labeled oven 1 or kitchen line 2, and flip it to the OFF position. Then go back to the oven and try to turn it on. If it's completely dead, you've done it right. If you're not 100% sure which breaker it is, flip the main. Shut down the whole kitchen if you have to. A few minutes of rebooting your POS system is infinitely better than a trip to the emergency room. Electricity is not a joke. It has no conscience. It will find the fastest path to ground, and if that path is through you, it will take it. So power off, breaker flipped, verified. That is our foundation. Everything we do from this point forward is built on that absolute certainty. Okay, the scene is secure. Let's begin the interrogation. Our multimeter is going to ask the heating element 2 very specific questions. The answer to these 2 questions will tell us everything we need to know. Question number 1. Are you whole? Is your path complete? In electrical terms, we're testing for continuity. Think of this heating element like a long, winding highway designed for electricity to travel on. When you send power to one end, it's supposed to travel all the way through that long, winding road inside, generating heat as it goes, and come out the other end. Continuity is just a fancy word for the road isn't washed out. It means there's an unbroken path from the start to the finish. If there's a tiny break anywhere inside that element, a crack so small you could never see it with your naked eye, the highway is closed. The electricity hits a dead end, and no heat gets made. So how do we test for it? Grab your multimeter. We need to set it to the continuity setting. It's usually marked with a symbol that looks like a sound wave, or a series of parallel arcs. The best way to know you're on the right setting is to touch the 2 metal probes of your multimeter together. If you hear a beep, you're in business. That beep is the multimeter's way of screaming, "Hey, I see a complete circuit. The highway is open." Now take your 2 probes and touch one to each of the 2 electrical terminals on the heating element. It doesn't matter which probe touches which terminal. We're just checking if a path exists between them. Press them on there firmly. What do you hear? If you hear a solid continuous beep, the same sound you heard when you touched the probes together, then congratulations. The element has answered yes to the first question. The internal highway is intact. The path is complete. But what if you hear nothing? Just silence. You double-check your connections, you press the probes a little harder, and still silence. That silence is your answer. The element is broken internally. The bridge is out. It's a dead end. No amount of electricity is going to make it through that broken path to generate heat. This element is guilty. Case closed. It needs to be replaced. There is no repairing a broken internal wire. Now a quick pro tip. Before you condemn the element, just touch your probes together again. Does it still beep? If not, the battery in your multimeter might be dead. It's a simple mistake that can send you on a wild goose chase. Always trust but verify your tools. Okay, so let's say our element passed the first test. We got a nice clear beep. It's whole. It's complete. So we're done, right? It must be innocent. Wrong. This is where so many people stop, and it's a critical mistake. We've only asked the first question. The second question is arguably even more important because it's a question of safety. Question number 2. Are you touching anything you shouldn't be? In electrical terms, we are testing for a short to ground. Let's go back to our highway analogy. The electricity is supposed to stay on the road inside the element. The metal casing of the element, the sheath, and the metal frame of the oven itself are like the guardrails and the surrounding city. The electricity should never, ever touch them. A short to ground happens when the road inside collapses and touches the guardrail. The electricity veers off its intended path and spills out into the metal frame of the oven. This is incredibly dangerous. It's what causes your breaker to trip instantly. The breaker is a safety device that sees that massive uncontrolled surge of power going where it shouldn't, and it slams on the brakes. In a worst-case scenario, if the grounding in your building is faulty, the entire metal skin of your oven could become energized, waiting for someone to touch it and become the path to ground. This is how serious accidents happen. So we have to check for it. The good news is we use the exact same setting on our multimeter. The continuity, the beep setting. This time you're going to place one of your probes on one of the element's electrical terminals. Doesn't matter which one. Now take your other probe and touch it firmly to the metal sheath of the heating element itself. Scrape it a little to make sure you get a good, clean metal-to-metal connection. What are we listening for? We are listening for silence. Silence is golden here. Silence means the internal highway is properly isolated from the guardrail. The electricity is staying where it belongs. If you get silence, that's a pass. Then, to be thorough, move the first probe to the other electrical terminal and repeat the test. Probe on the second terminal, other probe on the metal sheath. Again, we want beautiful, absolute silence. Now what if you hear a beep? If you put one probe on a terminal and the other on the metal casing, and that multimeter screams at you, you have found a serious problem. The element has failed the test. It is shorted to ground. It is actively leaking electricity to the frame. It is not safe. It is guilty and it needs to be replaced immediately. There is no negotiation. So let's recap the verdict. A good, innocent element will give you a beep when you test between the two terminals. And it will give you silence when you test between either terminal and the metal casing. It must pass both tests. One without the other is a fail. Think of it like a background check. You can't just be mostly good. It's all or nothing. Now I have to tell you about one more thing. A phantom. A ghost in the machine that can drive you absolutely crazy. What happens when an element passes both of these tests perfectly on your workbench? You get the beep, you get the silence, you reinstall it, power up the oven, and 10 minutes later, bam, the breaker trips. You pull the element out, test it again, and it tests perfectly. What is going on? You're dealing with a thermal short. This happens when there's a microscopic crack or weakness inside the element. When the element is cold, the crack is closed and it tests fine. But as it heats up and the metal expands, that tiny crack opens up just enough to make contact with the outer sheath, creating a short to ground that only exists when the oven is hot. It's one of the most frustrating problems to diagnose because the evidence disappears as soon as the element cools down. It's an intermittent failure, the boogeyman of oven repair. So how do you catch a ghost like that? Well, that requires a different strategy, and it's exactly what we're going to break down next. To catch a ghost, you can't just walk into the haunted house and ask it to appear. You have to set up your equipment, be patient, and wait for it to make a move. That's exactly our approach for an intermittent heating element. We're going on a stakeout. Your primary tool for this job isn't your standard multimeter, but its more capable cousin, the AC clamp meter, specifically one with a min/max or a peak hold function. Why the upgrade? Because a standard multimeter only gives you a snapshot in time. You touch the probes to a contact, you get a reading, and that's it. But our ghost isn't always there. It phases in and out of existence. Using a standard multimeter to catch an intermittent problem is like trying to photograph a lightning bolt by just randomly clicking the shutter. You might get lucky, but you'll probably just waste your time. A clamp meter with a max function, however, is like setting up a camera on a tripod and telling it to automatically take a picture the second it detects a flash of light. It watches for you. Here's the strategy. First, and I cannot say this enough, kill the power to the oven at the circuit breaker. Lock it out if you can. Safety is not a suggestion. Once you're absolutely certain the oven is dead, open your access panel to the heating element's wiring. You're looking for the two thick wires that connect directly to the element terminals. Pick one of them, it doesn't matter which one. Open the jaw of your clamp meter and place it around that single wire, making sure the jaw closes completely. It's crucial that you only clamp around one of the wires. If you clamp around both the hot and the neutral, their magnetic fields will cancel each other out, and you'll read 0 amps, even when it's working perfectly. Now, turn your meter's dial to measure AC amps, or A with a wavy line over it. Then, press the button for max hold or peak hold. This tells the meter, I don't care what the current is right now. I only want you to remember and display the single highest number you see from this point forward. With the meter clamped on and set, carefully position it so you can see the display from a safe distance. Make sure no part of the meter is touching any hot surfaces or moving parts. Now, you can go turn the power back on. Go to the oven controls, set it to a normal baking temperature, and start the cycle. Your job now is to just watch. When the oven first calls for heat, you will see a big number flash on the meter for a split second. This is called inrush current. It's the initial surge of electricity needed to get the cold element going, and it's perfectly normal. It might be 20 to 30% higher than the element's normal operating current. Your meter's max function will immediately lock onto this number. Don't be alarmed. Let the oven run for a minute to stabilize, then press the max button again to reset it. Now the real stakeout begins. Let the oven run through a full preheat cycle, and then let it maintain temperature for at least 15 to 20 minutes. A healthy element in a 240-volt oven might steadily draw, say, 15 amps. Your meter, with the max function reset, should now show a number very close to that 15 amp rating. If after 20 minutes you come back and the meter reads 15.5 amps, you're golden. The element is behaving. But if you come back and the oven is cool and the meter's display reads 28 amps, you've caught your ghost. That number means that at some point while you weren't looking, the current spiked dramatically. That spike is the internal short we talked about. The filament inside the element sagged, it touched the outer sheath, and for a split second it drew a massive amount of current before the connection broke again. That's your culprit. You have your evidence. The element is bad. Conversely, you can use the min function to catch a different kind of ghost. Let's say your oven heats up, but then shuts off randomly and won't come back on for a while. You'd clamp the meter on, start the oven, but this time you press the min button. This tells the meter to record the lowest reading it sees. If a healthy element is supposed to be drawing 15 amps, the lowest reading should be 15 amps. But if you come back and the meter reads 0.0, it means that at some point the connection completely broke. The filament inside the element stretched and opened up, the current stopped flowing entirely, and your oven went cold. Again, you've found your ghost. A bad element. This stakeout method is the single most reliable way to convict a failing component. It replaces guesswork with data. But what if you don't have a fancy clamp meter? Are you out of luck? Not at all. There's a lower tech, but still incredibly effective technique we use in the field. We call it the wiggle test. It's exactly what it sounds like, but it requires discipline and a strict adherence to safety. Once again, turn off the power at the breaker. Double-check that it's off. The wiggle test is performed with the power completely, totally 100% off. The theory behind this test is that many intermittent failures aren't inside the element itself, but in the connections leading to it. A wire terminal might be a little loose. A spade connector might have lost its tension. When the oven is cold, it makes a decent connection. But as everything heats up and expands, that marginal connection becomes a broken one. Then, as it cools and contracts, the connection is restored. It's maddening. So, with the power off and the oven cool, get access to the element terminals. Now, very methodically, you're going to physically check every part of the circuit. Grab the wire leading to the terminal. Wiggle it. Does it feel loose in the crimped-on connector? Grab the connector itself. Try to wiggle it on the element's terminal post. Is there any play? Does it slide off with almost no effort? It shouldn't. It should be snug. Follow that wire back as far as you can. Wiggle it at every junction point. Look for any signs of discoloration, melting plastic, or charring around the connectors. Heat is the byproduct of resistance, and a bad connection creates a lot of resistance. The connection itself will often get incredibly hot, long before the element does, and it will leave behind evidence in the form of burnt or melted insulation. I once had a call for a pizza oven at a small shop in Philly. It would work perfectly for the lunch rush, but die halfway through dinner service every single night. The owner had replaced the thermostat twice. Another tech had replaced the element. Nothing worked. I went in, killed the power, and started the wiggle test. The element terminal itself was solid. The wire felt fine. But I followed it back to a ceramic wire nut that connected it to the main harness. When I grabbed that ceramic nut, it literally crumbled in my hand into dust. It had been cooked for years. The connection inside was loose, and every night, as the oven hit peak temperature during the dinner rush, the wires would expand just enough to break contact. After it cooled overnight, it would work again for lunch. We replaced a 50-cent wire nut, and the problem was solved for good. The wiggle test is your physical inspection. You are manually trying to provoke the failure in a safe, powered-down state. If you find a loose spade connector, you can often just gently crimp it with a pair of pliers to tighten it up before sliding it back on. If you find a burnt wire, you found a much more serious problem that needs to be properly cut back and re-terminated. Between the clamp meter stakeout and the physical wiggle test, you now have two powerful strategies to hunt down the most frustrating type of failure. You're no longer just guessing. You're gathering intelligence, looking for evidence, and building a case. This is the difference between a part swapper and a technician. But what if you run these tests in the element and its wiring pass with flying colors? Your clamp meter shows a perfect, steady current draw. Your wiggle test reveals nothing but tight, clean connections. Yet, the oven still won't heat properly. This is where we have to expand our investigation. An oven is a system. The heating element is the muscle, but it does nothing without a command from the brain. If the muscle is good, we have to start questioning the orders it's being given. That means we have to look at the components that control the flow of electricity to that element: the thermostats, the relays, and the sensors. These are the oven's nervous system. And just like the element, they can fail in confusing and intermittent ways. Proving the element is good is just the first most important step. Now we have to learn how to interrogate the rest of the suspects. First on our list of suspects is the thermostat. Think of it as the general manager of your kitchen. It doesn't do the heavy lifting, but it tells everyone else when to work. It's a beautifully simple device at its core: a temperature-sensitive switch. Inside, there's either a bimetallic strip that bends with heat or, more commonly in commercial ovens, a capillary tube filled with a special gas. This tube runs from the control knob into the oven cavity. As the oven heats up, the gas in the tube expands. This expansion pushes against a diaphragm, which physically opens a set of electrical contacts, cutting power to the heating element. As the oven cools, the gas contracts, the pressure releases, and a spring pushes the contacts closed again, turning the heat back on. On off. That's how your oven maintains a temperature. Now, how does a general manager fail? In a few spectacular ways. The most obvious is that it just quits. The internal mechanism breaks, the contacts corrode, or the capillary tube gets damaged and loses its gas. In this case, the switch fails open. It never closes the contacts, never sends the signal to heat up. You turn the oven on and nothing. The lights might come on, the fan might whir, but you get zero heat. It's a cold, dead box. This is frustrating, but it's actually the easiest failure to diagnose. The far more dangerous failure is when it fails closed. The contacts get stuck together, welded by a small arc of electricity, or the mechanism just seizes up. Now the thermostat can't open the circuit. It's screaming more heat. More heat. Constantly. Your oven won't just reach 350 degrees. It'll try to reach the temperature of the sun. This is a runaway oven, a legitimate fire hazard, and the reason our next suspect, the high-limit switch, even exists. But the most common, most insidious, and most costly failure for a small business is when the thermostat simply lies. It loses its calibration. It gets old, the internal parts wear, and its sense of temperature begins to drift. Your dial says 400 degrees, but the oven is actually sitting at 350. Or worse, it says 350, but it's really 390. This is the ghost in the machine that ruins your product. It's why your bread isn't rising properly, why your pizzas have a soggy middle, why your pastries are burning on the edges. You're following the recipe perfectly, but the oven is betraying you. This single faulty component can slowly destroy your reputation, one inconsistently baked good at a time. So how do we prove the thermostat is the liar? We have to cross-examine it. The first, simplest test is the click test. With the oven cold and quiet, turn the thermostat knob up slowly from the off position. Somewhere, usually around the 100 or 150 degree mark, you should hear a faint but distinct click. That click is the sound of the internal contacts closing, the command to heat being given. If you don't hear that click, it's a very strong sign the thermostat's mechanicals have failed. But hearing the click does not mean the thermostat is good. Just means the switch is moving. It doesn't tell you if electricity can actually flow across those contacts, and it certainly doesn't tell you if it's clicking at the right temperature. For the real truth, we need our multimeter. First, kill the power to the oven at the breaker. No excuses. Then, access the back of the thermostat and carefully disconnect the two wires from its terminals. Set your multimeter to the continuity setting, the one that beeps. Touch one probe to each terminal on the thermostat. With the knob in the off position, you should get nothing. Silence. Now turn the knob up past that click point. Your meter should beep. You have continuity. This proves the switch is at least capable of opening and closing an electrical circuit. If it fails either of these tests, it's junk. Replace it. But what if it passes? That's when you test for the most common failure: inaccuracy. For this, you need an independent, reliable oven thermometer. Not the cheap one from the grocery store, but a decent one. Place it in the center of the oven. Now, reconnect the thermostat, turn the power back on, and set the oven to a common temperature, say 350 degrees Fahrenheit. Let the oven preheat completely. Don't just wait for the preheat light to go off. Give it a good 20 to 30 minutes to stabilize, allowing it to cycle on and off a few times. Now look at your independent thermometer. What does it say? If your dial is set to 350 and the thermometer reads 340 or 365, you're in good shape. But if it reads 310 or 400, you've found your culprit. That thermostat is lying and it's costing you money. Some high-end thermostats have a tiny calibration screw, but for most, replacement is the only surefire fix. Now let's talk about the thermostat's bodyguard, the high limit switch. This is a safety device and it is not optional. It's a simple, non-adjustable switch that's usually mounted right on the oven cavity. Its only job is to watch for a runaway temperature situation. If the main thermostat fails and the oven starts overheating, the high limit is set to trip at a dangerously high temperature, maybe 550 or 600 degrees, cutting off all power to the heating element and preventing a fire. If your oven is completely dead, no heat at all, the high limit is a primary suspect. Testing it is simple. Again, power off at the breaker. Locate the switch. It will have 2 wires. Disconnect them and test for continuity. At room temperature, it should always have continuity. It's a normally closed switch, designed to be invisible until a disaster happens. If your meter is silent, the switch has either failed or it has done its job and tripped. Some high-limit switches have a tiny red reset button in the middle. If yours does, you can try pressing it. If it clicks, it was tripped. But you are not done. I repeat, you are not done. A tripped high limit is a symptom of a much larger problem. It's the fire alarm going off. You don't just turn off the alarm and go back to bed. You find the fire. The fire in this case is almost always a failed closed thermostat or, as we'll see next, a stuck relay. Never ever just reset the high limit and assume the problem is fixed. Find out why it tripped. Finally, let's interrogate the muscle of the operation. The relay or contactor. Your thermostat is smart, but it's weak. It can't handle the massive electrical current your heating elements demand. Trying to run that much power through a delicate thermostat would melt it instantly. So the thermostat uses a small, safe amount of voltage to activate an electromagnetic switch called a relay or, for bigger jobs, a contactor. The thermostat tells the relay to turn on, and the relay, with its big, beefy internal contacts, connects the high-voltage power directly to the element. It's the bouncer that actually does the heavy lifting when the manager gives the nod. Like any bouncer, it can fail. The electromagnet coil inside can burn out. When this happens, the thermostat sends the signal, but the relay does nothing. You won't hear its characteristic clack or thunk. When the oven calls for heat, the element never gets power. The other, more common failure is that the high-power contacts inside get pitted, burned, or even welded together from the electrical arcing that happens every time they open and close. If they're pitted, they make a poor connection, leading to intermittent or weak heat. And if they weld themselves shut, they can't turn off. They will send power to the element continuously, creating that same runaway oven situation that trips the high-limit switch. You can often diagnose a relay just by listening. When you turn the thermostat up, you should hear a click from the thermostat, followed almost immediately by a much louder, more solid clack from the relay as it pulls in. If you hear the first click but not the second, the relay is a prime suspect. To confirm, and please be extremely careful, you can sometimes test for voltage at the relay's coil with the power on. If the thermostat is sending voltage to the coil but the relay isn't closing, the relay is bad. For a safer test, turn the power off. If you suspect the contacts are welded shut, check for continuity across the high-voltage terminals. They should not have continuity when the oven is off. If they do, they're stuck. Replace the relay immediately. So we have our chain of command. The thermostat, our manager, decides it's time to heat. It sends a low-voltage signal to the relay, our muscle, which closes its contacts and sends the high-voltage power to the element, our worker bee. And watching over the whole operation is the high-limit switch, the ever-vigilant bodyguard. If any one of them fails in their duty, the entire system breaks down. But what happens when all the components test perfectly, yet the oven still won't work? That's when you have to investigate the connections between them, the hidden world of burnt wires and loose terminals. And that's a whole different kind of investigation. This is where you put on your detective hat, because the clues aren't always obvious, and the culprit is often hiding in plain sight. We're moving beyond testing individual parts, and into understanding the system that connects them all. Think of it like this. Your heating element is a light bulb, your thermostat is the light switch, but the wiring is the hidden connection in the wall. If that wire is cut, it doesn't matter how good the bulb or the switch is. Nothing is going to happen. In a commercial oven, this wiring in the wall is a complex web subjected to intense heat, grease, and constant vibration. It's the oven's nervous system, and when it starts to fail, it can cause some of the most frustrating, intermittent, and hard-to-diagnose problems you'll ever face. This is the stage where many people give up and call a pro. But you don't have to. You just need to know what to look for. The first and most powerful tool you have in this investigation is your own eyes. Before you even think about grabbing your multimeter, you need to perform a thorough visual inspection of every wire and every connection you can see. Remember, always with the power completely disconnected at the breaker. Start by looking for the obvious discoloration. Wires in an oven, especially near heat sources, should be protected by high-temperature insulation, often made of fiberglass or silicone. If you see plastic insulation that's brown, crispy, or blackened, that's a 5-alarm fire of a red flag. It means that wire has been getting dangerously hot. This heat isn't usually from the oven's ambient temperature. It's generated by a poor connection. Electricity struggling to jump a loose or corroded gap creates intense, localized heat, like a tiny arc welder. It cooks the wire from the inside out, destroying the insulation and making the copper brittle. Gently, and I mean gently, touch the wires, especially near the terminals. Do they feel stiff and brittle? If a wire feels like a piece of dry spaghetti, it's a problem waiting to happen. That brittleness means the copper strands inside could be fractured. The insulation might look fine on the outside, but inside, the electrical path is broken. Next, look closely at the terminals themselves, the little metal connectors at the ends of the wires. Are they shiny and clean? Or are they covered in black soot, green corrosion, or a hazy film? Any of that is a sign of a bad connection. Pay special attention to the spade connectors that slide onto the tabs of components like heating elements and thermostats. These are notorious for vibrating loose over time. Give each one a gentle wiggle. It should be snug. If it feels loose or slides off with almost no effort, you found a major problem. That looseness creates resistance, which creates heat, which creates more resistance, in a vicious cycle that eventually leads to failure. This is the point where your multimeter becomes your best friend again, but we're going to use a different function: the continuity test. It's usually marked with a symbol that looks like a sound wave or a diode. When you touch the probes together in this mode, the meter should beep. All this beep means is that there is a complete, unbroken path for electricity to flow from one probe to the other. It's a simple yes or no question. Is this wire a solid road? Or is the bridge out? Let's put it into practice. Imagine your lower bake element isn't working. You tested the element itself and it has the correct resistance, so the element is good. You hear the thermostat click, so you know it's trying to send power. The problem must be the path between the thermostat and the element. With the power off, disconnect the wire from both the thermostat terminal and the element terminal. You are now holding a single isolated wire. Set your multimeter to continuity. Touch one probe firmly to the metal connector at one end of the wire, and touch the other probe to the connector at the other end. If you hear that beautiful clear beep, it means the wire itself from end to end is perfectly fine. The copper inside is unbroken. If the wire beeps but the element wasn't working, what does that tell you? It tells you the problem wasn't the wire itself, but the connection it was making at one of the ends. The terminal was likely loose, burnt, or corroded, preventing it from making good contact with the component. But what if you do the test and you get silence? No beep. That's your smoking gun. It means that somewhere between your two probes that wire is broken. It might be a fracture you can't see, hidden under the insulation. It doesn't matter where it is. The wire is bad and it has to be replaced. You'll repeat this process for every critical wire in the circuit you're troubleshooting. The wire from the power source to the switch. The wire from the switch to the thermostat. The wire from the thermostat to the element. It's a methodical process of elimination that lets you pinpoint the exact point of failure. Let's say you found the culprit: a burnt terminal on the end of a wire leading to your main heating element. You can't just slap some electrical tape on it and call it a day. That's not a repair. That's a fire hazard. You need to do it right. First, you'll need the right tools: a good pair of wire strippers and crimpers, and the correct replacement terminals. And here is a crucial pro tip. For any connection near a heat source, you absolutely must use high-temperature ring or spade terminals. They're made from nickel-plated steel, not the standard tin-plated copper. They're designed to withstand the heat cycles inside an oven without degrading. Using a standard automotive terminal here is a recipe for a repeat failure in a few months. Using your wire cutters, snip off the old burnt terminal. Cut back far enough to ensure you're getting to clean, unscorched copper wire. Then, use your wire strippers to carefully remove about 1/4 inch of insulation, exposing the fresh wire. Make sure not to nick or cut any of the copper strands. Twist them together tightly with your fingers. Now, take your new high-temperature terminal and slide it over the exposed wire. Make sure all the strands of wire are inside the barrel of the terminal. Now grab your crimper. Find the correct size slot for your terminal. It's usually color-coded. And place the barrel of the terminal in it. Squeeze the crimper with firm, steady pressure until it clicks or bottoms out. You want to create a solid, cold weld between the metal of the terminal and the copper of the wire. After you crimp it, give it the tug test. Hold the wire and pull firmly on the terminal. It should not budge. If it pulls off, your crimp was no good. Cut it off and do it again. A loose crimp is just as bad as the loose connection you started with. For an extra layer of professional protection, use heat shrink tubing. Before you crimp the terminal, slide a small piece of heat shrink tubing onto the wire. After the terminal is crimped and tug tested, slide the tubing up so it covers the barrel of the crimp and a small portion of the wire's insulation. Then use a heat gun. A hairdryer on high might work in a pinch, to gently heat the tubing until it shrinks down tight, creating a tough, moisture-proof and strain-resistant seal. This is far superior to electrical tape, which will just turn into a gooey mess in the heat of an oven. Now you have a connection that is likely stronger and more reliable than the one that came from the factory. Reconnect it to your component, ensuring it's snug and secure, and move on to the next suspicious wire. This is the meticulous, patient work that separates a parts changer from a true technician. It's about understanding that a system is only as strong as its weakest link. And in a commercial oven, that weakest link is almost always a connection that has been compromised by heat and vibration. By learning to read the clues, the subtle discoloration, the brittle insulation, the loose terminal, and by knowing how to properly test and repair these connections, you gain the power to solve problems that seem completely mysterious to the untrained eye. We've mastered the electrical nervous system, the flow of power and the signals that control it. But what if your oven runs on gas? The principles of control are similar, but the components are entirely different, and the stakes are even higher. Next, we're leaving the world of electrons and entering the world of molecules. As we dive into gas valves, pilot lights, and thermocouples, the heart of any gas-powered kitchen. The intricate dance of gas and fire is governed by a trio of components, each with a critical role. Think of it like this. If the electrical system is the oven's brain and nervous system, the gas system is its respiratory system. It breathes in fuel and exhales heat. And just like our own breathing, it has to be perfectly controlled because when it's not, the consequences can be catastrophic. Let's start with the gatekeeper, the main gas valve. This component is the absolute authority on whether gas flows to your burners or not. It's an electronically controlled valve that receives a signal, either from your thermostat or the main control board, and physically opens to allow gas to pass through. When you hear that satisfying thump or clunk a few seconds after your oven calls for heat, that's often the sound of the gas valve solenoid activating. It's a simple job, but it has to be flawless every single time. Failures in a gas valve typically happen in one of three ways. First, it can fail to open. You'll hear the call for heat, the fans might kick on, but you never get that clunk, and no gas flows to the burners. The oven remains cold. This can be caused by a bad solenoid coil on the valve itself, or a failure in the electrical signal telling it to open, which traces back to the issues we discussed in the last part. The second failure is less common but more dangerous. It can fail to close. The valve gets stuck open, and the oven keeps heating uncontrollably, blasting past its set temperature. This is an immediate shutdown situation. Kill the gas, kill the power. The third and most critical failure is a leak. Gas valves have seals and diaphragms that can wear out over time, allowing gas to seep out. This brings us to the single most important rule of working with gas. If you smell gas, stop. Stop everything. Don't turn anything on, don't turn anything off. The spark from a light switch or a thermostat clicking can be enough to ignite it. Get everyone out. Shut off the main gas supply to the appliance or the building, and call a professional. Your nose is the most sensitive and important tool you have. Never ever ignore it. Now, assuming the gas valve is working, it opens and sends gas toward the main burners. But what lights that gas? That's the job of the humble pilot light. The pilot is a tiny, constant flame that serves as the ignition source for the much larger main burner. It's the eternal flame of your kitchen, the tiny spark of life waiting for the signal to roar. For many business owners, the most common and frustrating problem they'll ever face is a pilot light that refuses to stay lit. You can light it with a match or a lighter. It burns beautifully for a few seconds, but the moment you let go of the gas knob, poof, it goes out. You might do this 10-20 times, getting more and more frustrated, thinking the oven is possessed. It's not. The oven is actually doing its job perfectly. It's protecting you, because the pilot isn't just a flame. It's part of a brilliant, simple safety system. And the hero of that system is a component called a thermocouple. The thermocouple is one of the most ingenious and important safety devices ever invented for a gas appliance. It looks like a simple copper wire with a small, bulbous tip at one end and a threaded connector at the other. But inside is a scientific miracle. The tip is made of two different metals welded together. When you heat the junction of two dissimilar metals, it generates a tiny amount of electricity, a few millivolts. It's not much, but it's enough. Here's how the whole system works together in a beautiful, safe sequence. The tip of the thermocouple is positioned so that it sits directly in the pilot light's flame. The other end of the thermocouple screws directly into the gas valve. When you press the pilot knob and light the flame, that flame engulfs the tip of the thermocouple. The heat generates that tiny electrical current, which travels down the wire to the gas valve. Inside the gas valve is a tiny electromagnet. That minuscule voltage from the thermocouple is just enough to power that magnet, which holds a small safety valve open, allowing gas to continue flowing to the pilot. So when your pilot light won't stay lit, it's almost never the pilot's fault. The pilot is just a tube. The problem is that the gas valve isn't getting the electrical, all-clear signal from the thermocouple. The moment you release the knob, the safety valve inside snaps shut because the electromagnet isn't energized, and the flame goes out. The oven is essentially screaming at you. I don't see a flame, so I'm shutting off the gas before we all have a very bad day. Why would the thermocouple fail? Over time, the tip can get covered in soot and carbon, which insulates it from the flame, preventing it from getting hot enough. Sometimes you can gently clean it with a bit of steel wool or a soft wire brush and bring it back to life. But more often, after thousands of heating and cooling cycles, the metal fatigues and it simply stops producing enough voltage. You can test this with a multimeter set to DC millivolts. A healthy thermocouple should produce somewhere between 20 and 30 millivolts when heated by the pilot flame. If you're getting less than 15, or the reading is erratic, it's time for a new one. And here's the best part. Thermocouples are incredibly cheap. They are a $5 to $15 part. They are, without a doubt, the number one thing you should have as a spare in your restaurant's emergency toolkit. Replacing one is usually as simple as unscrewing the old one from the gas valve and its mounting bracket, and screwing the new one in. Just be careful not to over-tighten it. Finger tight plus a quarter turn with a wrench is usually all you need. 90% of pilot won't stay lit service calls can be fixed in 5 minutes with this single inexpensive part. It's the most empowering first repair a small business owner can learn. Now, sometimes you'll see a thicker, more robust version of a thermocouple. This is called a thermopile. It's essentially a bundle of many thermocouples wired together in series. It does the exact same job, proving the pilot flame is lit, but it generates a much higher voltage, around 500 to 750 millivolts, or 3/4 of a volt. This higher power is often used in ovens that don't rely on external electricity to operate the main gas valve. The thermopile itself generates enough power to run the whole system. The troubleshooting is the same. If the pilot won't stay lit, or the main burner won't ignite, the thermopile is a prime suspect. So let's put the whole puzzle together. You turn the oven on. The thermostat calls for heat. This sends an electrical signal to the main gas valve. But the gas valve won't send gas to the main burner until it gets a second signal, the safety signal. That signal comes from the thermocouple, which is sitting in the pilot flame, constantly generating a tiny voltage that says, "Yep, the pilot is lit. It's safe." Once the main gas valve has both the call for heat and the safety signal from the thermocouple, it finally opens, sending a rush of gas to the main burner, which is immediately ignited by the waiting pilot flame. The oven roars to life. It's a chain of command. Every link must be perfect. When troubleshooting a gas oven that won't heat, this is your workflow. First, is the pilot lit? If yes, the problem is likely upstream, the thermostat, the main valve, or the electronics. If the pilot is not lit, then your focus shifts entirely to the pilot system. Can you light it manually? If it won't stay lit, your first suspect is always the thermocouple. If the thermocouple is good, check the pilot tube itself. Spiders love to build nests in there, and a tiny bit of debris can block the flow of gas. You can often clear it with a thin piece of wire or a blast of compressed air. Understanding this relationship between the valve, the pilot, and the thermocouple demystifies the entire gas side of your oven. It's not black magic. It's a simple, elegant system designed with safety as its #1 priority. And by knowing how to diagnose it, you're not just fixing an oven. You're taking control of the very heart of your kitchen's production. You've now conquered the electrical brain and the gas-powered heart of your oven. You understand how it thinks and how it breathes. But knowing how to perform surgery is only half the battle. The true professional, the truly profitable business owner, knows how to prevent the patient from ever getting sick in the first place. Next, in our final part, we're going to assemble the ultimate commercial oven first aid kit, and I'll give you the bulletproof maintenance checklist that will stop these problems before they ever start, saving you thousands of dollars and countless hours of downtime for years to come. Alright, let's start with the first aid kit. And I don't want you to think of this as just a toolbox. This is your business's emergency response kit. It's the difference between a 10-minute fix and a 2-day shutdown. Having these items on hand, organized, and ready to go is a non-negotiable for anyone serious about keeping their kitchen running. First, the basics. Your hand tools. You need a dedicated set that lives in the kitchen, not one you have to borrow from your garage. Get a multi-bit screwdriver with a good grip. You'll want Phillips heads, flatheads, and crucially a set of Torx bits. Many commercial appliances use these star-shaped screws to keep amateurs out, but you're not an amateur anymore. Next, a set of adjustable wrenches, a small and a large one, a good pair of needle nose pliers for getting into tight spots, and a pair of lineman's pliers for gripping and cutting thicker wires. Finally, a decent socket set, both metric and standard. You don't need a massive mechanics set. Just a basic one will cover 90% of the nuts and bolts you'll encounter. Now for the real game changer, your diagnostic tools. The #1 most important tool you will own is a multimeter. It is your X-ray vision. It lets you see electricity. It tells you if power is getting where it needs to go, if a component has failed, if a switch is broken. Learning to use the basic functions, continuity, voltage, and resistance, is the single most empowering skill you can develop in equipment repair. We've talked about it throughout this series, and for good reason. It turns guesswork into a diagnosis. Alongside it, get a non-contact voltage tester. It's a small pin-like device that beeps or lights up when it's near a live wire. It's a 5-second safety check that can literally save your life before you even touch a single screw. Next up, the essential spares. These are the common consumables, the parts designed to fail over time. Having them in a drawer is like having an insurance policy that actually pays out. Start with fuses. Look at the fuses in your oven's control panel. Note the amperage and type. They're usually glass tube fuses, and buy a multi-pack. A blown fuse can shut you down completely, and it's a 50-cent part. Next, a universal thermocouple or a specific one for your model. As we've seen, this is one of the most common points of failure for gas ovens. An igniter. If you have a glow bar or a spark ignition system, that igniter will eventually wear out. It's not a matter of if, but when. Having a spare means you're back up and running in under an hour instead of waiting for a part to be shipped. A spare door gasket. A worn-out gasket bleeds heat, skyrockets your energy bill, and creates inconsistent bakes. Swapping one out is easy and provides an instant return on investment. And finally, the right kind of high-temperature oven light bulbs. It seems minor, until you're trying to check on your product in a dark, cavernous oven. Last part of the kit, safety and cleaning. A pair of thick, heat-resistant gloves. A pair of sturdy work gloves. And safety glasses. Never ever work on equipment without them. For cleaning, a putty knife for scraping, wire brushes for cleaning burner ports and rack guides, and a good commercial-grade degreaser. Because a clean oven is a happy, efficient, and safe oven. So there it is. Your first aid kit. Build it this week. Put it in a dedicated bag or box. It is your key to immediate, decisive action. But now, let's talk about how to make that first aid kit collect dust. Let's talk about prevention. This is the bulletproof maintenance checklist that will transform you from a firefighter into a strategist. We'll break it down by frequency. Daily, weekly, monthly, and annually. Your daily tasks. These should take less than 10 minutes at the end of every single day. 1. A full wipe down of all exterior surfaces. 2. Clean the door glass inside and out. 3. Remove the oven racks and quickly scrub off any major debris. 4. Wipe down the door gasket with a damp cloth. This removes grease and food particles that can degrade the seal. This simple habit can double the life of your gasket. 5. As you power down, listen. Just for a few seconds. Do you hear any new sounds? A squeak, a rattle, a hum that wasn't there yesterday? Your ears are an incredible diagnostic tool. Now for the weekly tasks. Set aside 30 minutes on your slowest day. 1. A deeper interior clean. Use that degreaser and a scrub pad to tackle any carbon buildup on the walls and floor of the oven. Carbon buildup creates hot spots and is a fire hazard. 2. Perform a thorough inspection of those door gaskets you've been wiping daily. Look for any rips, tears, or spots where they've become hard and brittle. Do the dollar bill test. Close the door on a dollar bill. If you can pull it out easily, your gasket is failing and it's time to replace it. 3. For gas ovens, inspect the burner ports. Make sure they're all clear of debris so you get a clean, even blue flame. Use a wire brush or a paper clip to gently clear any clogs. 4. Calibrate your thermostat. Place a reliable oven thermometer in the center of the oven. Set the oven to 350 degrees Fahrenheit. Let it preheat for 30 minutes, and check the thermometer. If it's off by more than 15 degrees, it's time to recalibrate, a process we covered in Part 6. On to your monthly checkup. This is where we get a little more technical. 1. A full safety system check. Test your door switches. Open the door while the oven is running. The fan and heat should immediately cut out. If they don't, that switch is a critical failure point that needs immediate attention. 2. Inspect any visible wiring. With the power off and unplugged, look for any frayed, cracked, or discolored wires, especially around the door hinge where they flex. 3. For convection ovens, listen to the fan motor. Any squealing or grinding sounds indicate the bearings might be on their way out. If there's an access panel, check the fan belt for cracks and proper tension. 4. Clean your ventilation system. This includes the filters in your hood. Clogged filters restrict airflow, which can affect oven performance and create a dangerous, greasy fire hazard in your kitchen. Finally, the annual or semi-annual plan. There are some things you should still call a professional for. Think of this as a doctor's checkup for your oven. Once a year, have a qualified technician do a full combustion analysis on your gas oven to ensure it's burning safely and efficiently. Have them check the gas pressure and perform a full, deep inspection of the control boards and internal components. Investing a few $100s for this preventative checkup can save you from a multi-thousand-dollar emergency replacement down the line. It's not a sign of defeat to call a pro. It's a sign of a smart business owner who knows where the limits of DIY are and respects the complexity of their equipment. And with that, we've come to the end of our journey. Think about where you were when you clicked on Part 1. Maybe you were facing a broken oven, feeling stressed, powerless, watching your profits tick away with every minute of downtime. Look at you now. You understand the core systems. You know how to diagnose a pilot light that won't stay lit. You can confidently test a heating element. You know the difference between a thermocouple and a thermostat. You are armed with a first aid kit and a maintenance checklist that puts you in the driver's seat. This series was never just about nuts and bolts. It was about a mindset shift. It was about taking one of the most intimidating, mysterious, and critical pieces of equipment in your business and turning it into something you understand, something you can control. Your oven isn't just a hot box. It is the heart of your kitchen. It's the engine of your profitability. And just like any high-performance engine, it requires respect, attention, and proactive care. The confidence you've gained here doesn't just apply to your oven. It applies to your fryer, your mixer, your walk-in cooler. You've learned a new way of looking at your kitchen, not as a collection of appliances that can betray you at any moment, but as a system that you can manage. You have the knowledge. You have the plan. The only thing left is action. Build your kit this week. Print out that maintenance checklist and post it on the wall. The next time your oven stumbles, you won't feel that panic. You'll feel prepared. You'll take a deep breath, grab your multimeter, and you will know exactly what to do. Thank you for investing this time in yourself and in your business. It will pay dividends for years to come. You are no longer just a baker, a chef, or an owner. You are the guardian of your kitchen. You are the first responder. You are in control. Now go and keep the heart of your business beating strong.